Ladies and gentlemen, welcome to the December meeting of the Royal Astronomical Society of Canada. Table of contents slide, please. We have a slightly unusual program for you tonight. We have the annual general meeting, which was for members, but members of the public are invited. Just please don't vote. And afterwards, we have our regular tasting fare of observations that you can do for yourself, observing challenges, 2 real science talks, including a special talk by Simon Hanmer, who we like so much we've given him his own special talk, special font. Starting our observation program tonight, we're going to have Steve McIntyre to tell us about what we can observe in the next month. Steve?
Which one's live here? Oh, I got the microphone in my hand. Did you see the moon on the way in? Yeah. Right? It's the first astronomical object I've seen in weeks, it seems. Anyway, there's a lot more great stuff in December. I'll point out a couple of the old standards for those that are new to astronomy. They're a must-see, and for old hands, they're always worth another look. And there's lots more great targets. I'll just get you started. All right, what am I doing here? That one? Yep. So starting about 8 o'clock mid-month, which is kind of around 9 o'clock at the beginning of the month and 7 by the end of the month. So, mid-month, 8 o'clock, the skies will look something like this. Jupiter, we have setting into the west, dominating the sky at magnitude a little bit brighter than -2. By the end of the month, it sets at 8:30, so it's pretty well your last chance, although it still presents quite nicely. Small telescope, you can definitely resolve the disk, and on good seeing, you might see a few cloud bands. Binoculars, and a steady hand, you can pick out the moons. We have, at the top, we have fairly bright star Deneb marking the tail of Cygnus, which lies across the Milky Way. And then high overhead, we have Cassiopeia. Center stage, we've got Pegasus and Andromeda, and we'll talk about the Andromeda Galaxy in a bit. Below that, we have Pisces and Cetus. On the charts, they look fairly obvious, but they're actually quite hard to see. The brightest star in Pisces is magnitude 3.8, and most of them 4 and below, so it's actually quite challenging to see from anything but a fairly dark sky. Cetus fares a little bit better with a single magnitude 2 star at the bottom. Most of the others are 3.8 and dimmer as well, and it's also lower, making it hard to see. Fomalhaut down at the bottom, a little bit southwest. In the southern fish, it's actually a fairly bright star as well at magnitude 1.2 or 1.1. But at 7 degrees above the horizon, it's also fairly challenging to see, but if you had a clear view, it's fairly obvious. We have, Aldebaran, a nice orange star, quite bright, marking the bullseye. And the brightest star in the open cluster, the Hyades. It's actually visually part of the cluster. It's actually half the distance from the rest of the star clusters. And then high overhead, we have Capella at I think 0.06. It's the brightest star at this time of night. And then rising in the west, we have Orion. We have Betelgeuse, I'm never quite sure, as a red giant. Let's see. I want to get the magnitude right. You can never remember all of these facts. So 0.43, so it's quite bright. And as a red giant, it's huge. I think it's ranked as one of the largest stars that they measure the diameter at 667 times the diameter of our Earth, so a rather large star. And then at the bottom, we have Rigel, another large reddish star at magnitude 0.15. It has a companion at magnitude 6.8. And separated by 9 degrees, but the difference in magnitude make them challenging. But if you can see them, it's quite nice because there's also a very distinctive difference in color. M33, fairly large galaxy just off the tip of Triangulum. Triangulum is actually fairly easy to see. It's a very distinctive small constellation. It's the third largest constellation in the local group at magnitude 5.7, and it's actually quite large at over a degree long and 42 arc minutes wide. It's will fill, well, you'd think it would fill the frame of view. And at magnitude 5.7, it would seem quite bright, but that huge area, that's twice the width of the moon. That brightness is spread over a large surface area, making it a rather challenging object to see. It's too dim or just below the threshold to be able to see unaided. In binoculars, it will show up as a distinctive fuzzy patch, and in a small scope, more or less the same. A large scope at low magnification, some structure starts to show up, but as soon as you go up, like 20 or past 20 or maybe 40, then the low contrast, the spiral arms tend to disappear in the background. So it's really an object for low power, small scopes. All right, so that's a photograph view of, it's described as a loose spiral galaxy, more or less edge on to us. M31, probably the most famous galaxy that just off the tip of Pegasus, a couple of stars over. It's the largest galaxy in the local group, the Milky Way being the second, so making the trio in the local group of the largest one. It's huge, 3 degrees wide and one, or long and 1 degree wide. It's a spiral galaxy tilted quite a bit towards us, giving it that oval shape. But the 3 degrees is the photographic view. Binoculars, probably you're lucky if you can catch like a half a degree, which is still a very large object, a half a degree of the central core, and maybe a degree and a half in a small scope, which is well enough to fill the frame, fill the view at low power. And at a dark site, you actually do get to see the whole thing in like a magnitude 20 in a 7mm scope. It just fills the whole field of view. So it's the furthest object that you can see unaided. Original estimates had it at 2.2 million light years, and the revised number is 2.9 million light years. And even in a moderate sky, I'm at magnitude 3.5 or 4 in my neighborhood, and I can see it in the sky, and in a dark sky, it jumps right out. Right. So then we've got its companions M110 and M32. From the photograph, it kind of looks like M32 is swamped by the larger galaxy, but in a small scope, there's actually quite a bit of black space. And so if you're looking for it, don't expect these things to sort of overlap and look crowded. They're actually quite far apart when you're looking at it through a telescope, especially a small telescope. M45, the Pleiades, or the Seven Sister. This is by far my favorite object in the night sky. Maybe it heralds in the winter constellations, or just winter. I like winter, but it's just a fun object to see. It's quite simple, but also a lot of fun and very distinctive. It's described as an open cluster with several hundred stars down to magnitude 9 or 10, but it's dominated by a dozen quite bright stars. The Seven Sisters, they are all sort of magnitude 2 to 5.6, and even on a moderately dark sky, you can probably pick out 6 or 7 of them. So the challenge is unaided to see how many you can pick out. There's claims, perhaps exaggerated, of people with excellent eyesight, I would imagine, picking out 14 of the stars in a dark site, but that would be over magnitude, or dimmer than magnitude 7 to do that. The brightest stars are hot blue stars, and in a photographic view, or in a telescopic view, in my opinion, the blue against the black provides an extra contrast, and they just sort of jump out. So to me, it's quite a spectacular object. And unlike a lot of astronomical objects, they don't just get fuzzier. You look through the telescope at this one, and it sort of jumps right out. So there's actually the 8 or 9 of the brightest stars, where it's sort of forming a little dipper. It's an object for binoculars, really. It's a fairly wide object. Not sure if I mentioned it there, but yeah, so it's spanning a degree or two. Better in binoculars or a small telescope at low magnification. In a photographic view, a better photograph than mine, the reflection nebula starts to show up as sort of a whitish or blue tinge as the dust collects or reflects the star from the hot blue stars. December 18th is an excellent chance to catch Mercury. I think it's at greatest elongation, but it's at least it's quite a bit from the sun. It's almost 20 degrees from the sun at that point, which is about an hour and 20 minutes behind the sun. So here at about 30 minutes after sunset, we have Mercury and a 2-day-old moon. So the moon provides an excellent reference point as well as a nice photo op there. So we got 6 degrees above the horizon, you'll find Mercury, and another 6 degrees past that is the moon. You should plan your outing in advance to find a site with a good western horizon, and plan on showing up around just around sunset. And the challenge is to see when you can see Mercury with unaided. Don't use binoculars because that's cheating, and it'd be a lot easier to see. Anyway, so that's an excellent photo op there. Anyway, so there's lots more to see. Those some of the highlights. Just some dates and times. We have a presentation coming up in the Geminids, so we'll talk about that. Mars, for people that observe in the wee hours of the morning, it's you can get a first look at Mars at transit at about 4 in the morning. And Saturn is rising just before 1 o'clock in the morning, so you can get a peek at that if you're up in the wee hours of the morning. And there we have it.
There are 100 billion stars in this galaxy, all buzzing around the central black hole, but you need an attention span of about 10 million years to appreciate the visual phenomenon. I don't have an attention span that long. I can last maybe 30 seconds. Now, luckily there are a few astronomical phenomena for people with short attention spans like me, and one of the quickest is meteors. And please welcome Pierre Martin, our active meteor observer, to tell us how to do it.
Thanks, Attila. I'll start. Okay, well, I've been up quite a few times to talk about meteors this year, and I just couldn't help myself. It's been an exceptional year for meteor showers, starting with a very strong return with the quadrantids in January, and then we had a triple outburst of Perseids in mid-August, which made the Perseids the strongest Perseid shower since the early 90s. And then we had some mild enhancements from both the Orionids and then the Leonids just recently in November. And we're not done yet. We still have the Geminids right around the corner, just a little bit over a week and a half from now. And by all means, it's an exceptional year for the Geminids for two big reasons. It's going to be new moon conditions, so that will ensure that the skies will be completely dark all night. And the Geminids are scheduled, according to the International Meteor Organization, should peak right at midnight our time. So we're very, very well positioned to see the meteor shower right at its best. So let's have a quick look at what we have here. So the main night for the Geminids is Sunday, the evening of the 13th, going into the morning hours of the 14th. It's currently the most reliable of all annual meteor showers and a favorite of many observers, even more so than the Perseids. Now, of course, the Geminids are not as widely observed as the Perseids for one big reason is that the cold weather tends to keep a lot of people inside. And also, December doesn't have quite nearly the same amount of clear skies as August typically has. But however, the Geminids can reach very high rates, well over 100 per hour, sometimes 120 to even 150 per hour under very dark skies, assuming the radiant in Gemini is very high up in the sky. And these are gorgeous meteors. If you haven't seen the Geminids yet, make yourself a favor and go out to see them. They produce nice medium-speed meteors. They enter the Earth's atmosphere at only 35 kilometers a second, which, as far as meteors go, is relatively slow compared to the zippy Leonids and even the Perseids. And they often exhibit some very nice colors, very vivid colors, sometimes bluish green meteors. Almost kind of looks like Christmas ornaments just gliding across the winter sky. Can be really quite a sight. And then the Geminids can be seen all night. Can be seen as early as 6 in the evening and as late as 6 a.m. in the morning, which is unusual since a lot of the other showers are best typically after midnight. Now, of course, the best time for the Geminids, the time where you're going to see the most out of the shower, is any time shortly after midnight into the early morning hours. So that would be the best bet. So if we look at 2008, just a summary of what happened last year, it was the circumstances weren't very good. There was a nearly full moon up, and despite the very strong moonlight, there was still a large amount of observations that the International Meteor Organization received. There was a lot of data that came in nonetheless, so they were able to get a good profile of the shower's duration. So we can see here that the Geminids typically start their activity in early December, around the 6th, 7th, is when we can start to see the first few Geminids, only maybe 2 or 3 per hour. And then as time goes on, the rates slowly start to ramp up until they reach a maximum right on the morning of the 14th. And notice after the maximum, the rates actually drop quite sharply down. So there's actually a slower buildup to maximum activity and the sharp drop-off. The Geminids are actually a transient meteor shower. They were discovered fairly recently in the 1860s, which is fairly new for a meteor shower compared to, say, the Perseids, which were observed for thousands and thousands of years. Now, what we notice is that in the late 1800s, the Geminids were actually a weak meteor shower. They produced only a few meteors per hour. And then as the 20th century kicked in, there was an increase, a gradual increase up to 30 per hour. And then in the 1950s, the rates were up to about 80 per hour, and it kept increasing since. According to a recent study by Peter Jenniskens of the NASA Meteoroid Center, he believes that the Geminid stream is actually tilting slightly and actually moving very slightly from the Earth's orbit. But as it turns out, his study shows that the Geminids will probably keep intensifying every year until they reach a maximum in 2050, where he believes the rates will be on average of 200 per hour. Now, I'm just going to backtrack where we were. On the next slide, you're going to see, we're going to zoom in right on December 14. So we're actually going to see the peak here in detail. And this is what it looks like. So you can see for several hours on December 14, and this was the case in 2008, the Geminids actually reach a sort of plateau of high activity over 100 per hour on the ZHR scale, which stands for zenith hourly rate. And for several hours, it's actually quite a broad peak compared to some of the other meteor showers. So even though the Geminids are scheduled to peak at midnight on the evening 13th, morning 14th, any hours surrounding midnight will probably produce equally high rates because of the broad nature of the maximum rates. And last year there was this unusual spike right here that shot almost up to 200 per hour, which is very unusual. So this was definitely not something that was expected. Normally the Geminids reach this sort of plateau that can sort of hover around 120 per hour under ideal skies, but this was definitely something kind of strange. So this makes it maybe perhaps even more exciting to see what's going to happen this year. Now, if we look at the sky on the evening of the 13th, very early, so right around at supper time at 6 o'clock, This would be the time where you're not going to see a lot of Geminids. You're going to see, at best, maybe only maybe 4 or 5 in the hour, the first hour after sunset. But what it would be very special to see during that period is the Earth grazers. Those, because the radiant in Gemini is going to be very, very low near the horizon, any meteors shooting out in the sky would appear to basically skim the Earth's upper atmosphere and produce very, very long paths that could persist maybe up to 2/3 of the entire sky. Almost looks like kind of like the version of a rock skipping on a pond. You see that meteor just keep going and going and going, and seeing only 1 or 2 of these can be really breathtaking and be the highlight of the night. So I would recommend that you start viewing for these early Geminids as early as you can, as soon as it gets dark, even 5:30, when it's not completely dark, but dark enough to see most of the bright stars. And from there, keep your eyes peeled in the sky for about an hour or so. The trick is not to look down where the radiant is located. Typically, I find that Earth grazers tend to skim sort of halfway up, either in the north or the southern sky. So sort of look towards where the Ursa Major and Ursa Minor is, so to just scan the skies in that area, or in the south, in that area here. And if the rates should be strong enough that if you're patient, you will likely see a few of these Earth grazers. Now, if we move in, the best activity is going to be around midnight, between midnight and 3 o'clock, I would say. Now, the radiant, which is located very close to Castor and Pollux, the twins in Gemini, is where all the meteors are going to seem to sort of trace back from in the sky. And you'll notice that the higher the radiant moves up in the sky, the more meteors will seem to drop all around the sky in every direction, mostly shooting straight down to the horizon. So definitely, as the radiant moves higher and higher up in the sky, the number of meteors will increase until the radiant reaches its culmination, its highest point in the sky, at about 2 o'clock in the morning. So with the peak of the Geminids being at midnight and the radiant's maximum elevation at 2 a.m., my best guess is that the best of the Geminids will be anytime between midnight and 3 o'clock in the morning. If you're not planning to stay up all night, definitely set up your alarm to wake you up. Now, what's very unusual about the Geminids is that they are just about the only major shower known to be associated with an asteroid. This is highly unusual because, as far as we know, all the other known showers are caused by comets, and not in this case. It's asteroid 3200 Phaethon. Its discovery was in 1983, and it's a fairly sizable object, about 5 kilometers in diameter. What makes it very unusual is that it actually comes very, very close to the sun. It actually comes in closer than half the distance from Mercury and the sun. So this makes it a very close approach to the sun when it swings by. Now, what happens is, so how can an asteroid cause a meteor shower? There's been a number of theories about that over the years. But as it turns out, the most likely cause is that Phaethon is actually an extinct comet. It's a comet that came back so many times around the sun that it actually burnt out, vaporized all of its volatile material, all of its crumbly dust matter, basically disappeared. So all there is left is an object, a comet that actually looks like an asteroid because it no longer produces any visible tail, any visible coma. It's just a dark gray object. And it definitely shares the same orbit as all the Geminids around the sun. So this makes it quite an unusual case. And on that matter, what researchers have noticed is that Geminid meteors don't exactly look like the meteors of other showers, in such that even the bright Geminids are very smooth in the sky. They don't produce very many flares. They sort of just gradually flare up and then flare out. And they realize that the Geminids are also sort of not very crumbly. They're not very hard either. They're not like a stony object, but they're definitely in between. And what happens is that the Geminids, just like the parent comet, I should say asteroid, Phaeton, comes really close to the sun, all the Geminids do the same. They actually swing very close, and the Geminids actually get baked by the sun. So they actually turn a bit harder, which produces these differences, this unusual look in the meteors that we see every December. Okay, so when you're out looking for Geminids, what you'll notice is not every meteor actually radiates from the, or streams from the radiant, which is near K-Star and Pollux. There's actually a number of other minor showers active, which we have here. The anti-Helian source, which is more an artificial radiant caused by sporadics that are incoming towards the sun. And then we have the monoceratids, which produce maybe about 3 meters per hour of average speed. And then the sigmohydrids, which can produce about 5 per hour, but would be very swift meteors. So there's if you're out for a little while, you're definitely going to see some meteors that are coming from different sources. And of course, there's the purely random meteors, the sporadics, which are not associated with any of the known active meteor showers. So a few tips to get the best out of the Geminids this year. Keep in mind that the maximum is very broad. So even if the Sunday night, the peak night, is clouded out, keep in mind the night before, which should be ramping up fairly nicely. My recommendation is if you go out on the Saturday night, try to get out as late as you can in the night, after 2 o'clock in the morning, where the rates should be somewhere around 40 per hour in dark skies. If that doesn't work, and if the maximum night doesn't work, the night after, the Monday night, evening of the 14th, should still produce some reasonable activity. Now, as I mentioned earlier, the Geminids definitely have a sharper drop-off after the peak, but you should still see enough, something interesting the following night. If you're not up all night, make sure your alarm is set and actually working. I don't know how many times that I intended to do that and woke up and it was in the middle of the morning. I totally missed my meteor shower because of a failed alarm clock, so don't get caught with that. As I mentioned earlier also is try to avoid staring right into the radiant, because actually this actually tends to be a less interesting area because the meteors that are coming in that direction are actually coming straight to you. And of course they're very high up and they all burn up high in the atmosphere. But you'll see meteors coming further out, further away from the radiant to be longer and actually easier and probably more aesthetic. And meteors can actually happen anywhere in the sky. There's no specific best area to look. Darkness is definitely a big important factor. Try to get out to the darkest spot you can. If you can get out of the city to a dark site like the FLO, that would be the best bet. If not, try to get to a dark area, either a dark corner of the backyard where you don't have a bright light in view. And fortunately, the Geminids do produce a lot of bright meteors, and they can actually be enjoyed fairly reasonably even from a suburban sky site. Of course, December nights, if it's clear, it will probably get quite cold, so make sure that you're prepared for that. Keep comfortable. The best way to observe meteors, it doesn't take much. Just take your favorite lawn chair out, a nice warm sleeping bag, and just get yourself comfortable and look up. Basically, you just need to relax your eyes and sort of try to, of course, you cannot see the whole sky all at once, so you can only see a small section at a time, but try to scan, sort of move your eyes around, and you'll definitely see meteors and come in spurts. You'll be having moments where you'll see maybe nothing for several minutes, and then you'll see a burst, several meteors, perhaps in as little as 1 minute. And of course, keep safe. If you can, try to observe with company. Grab some friends and go out together, especially in December, being it can be cold nights, and you want to keep that in consideration. And of course, if you're out with a group or you have newcomers with you, have a green laser handy to point out stuff, which can be a lot of fun. And finally, if you're ambitious, you can try your hand at meteor photography. It doesn't take much fancy equipment, just a camera set up on a tripod. Do time exposures, set up your lens, your wide-angle lens, as fast as possible, preferably f2.8 or faster. and set up your ISO on the camera to ISO 800. You might want to do some testing depending on the darkness of your skies. Here are my results of the 2006 Geminids. That was my last, my best shot at them. That was my mad dash down to Tennessee that year to see them. And it was a great meteor shower. That year I was able to count over 700 meteors in a span of 7.5 hours. And that was a night when the maximum came very late in the early morning hours, when the radiant had already passed the highest point and was actually descending into the west. So if the weather is good this coming on the 13th, the conditions should be even better. And someone who wants to pull a marathon and stay up all night, I might even possibly get as many as 1,000 meteors, but that's if you're willing to stay up for 12 hours. And then this here is a composite, so I took several short exposures and stacked them together in Photoshop, every exposure containing meteors in that area, and you can see them streaming down towards the horizon at a time when the radiant was very high up in the sky. And there's a couple of sporadics. There's one that you can see here that's traveling against all the flow, so definitely coming from a different direction in the sky. And this was in 2007. So that year, the peak night was actually clouded out, so I missed that completely. But I did have a clear night the following night, and it turns out that although the rates were only about 20 per hour, there were most of these meteors were very bright. And there was almost no faint meteors, actually, which was really neat to see. And my camera successfully captured these 4 bright Geminids. And that wraps up the Geminids, but I have something else I just wanted to announce. A bit of an observing report. As I was out on, I was heading out on November 16 for the Leonids. Just before 9 o'clock, 2 minutes before 9 o'clock, I was lucky to see a very bright fireball right in front of me in the windshield of my car, and it was just an incredible sight. And I can't take credit for this picture. It was taken by Andres Gada from Oak Heights, just southwest of Ottawa. But this definitely caught my attention because it definitely is the same meteor photographed from a different location. And what really caught my attention with this meteor is that, first of all, it was very bright. I estimated the brightest portion to be about magnitude -8. But it also, in my opinion, had all the right parameters to have possibly dropped some meteorites. And by that, it was, as far as I could tell, it was a sporadic. It wasn't coming from any of the known shower radiants that at least I was aware of. So that would imply that it was not cometary matter, but something perhaps more significant, like a stony object. It definitely had this very long path, almost Earth grazer, so it would have had a very shallow angle, and it moved slowly. And there was no flaring, as you see on this picture, no obvious explosion or breakup that would mean that the meteor would have disintegrated quite wildly. So these are all signs that possibly something might have dropped to the ground as fragments. Now, what I did is I studied this picture, looked at the meteor against the stars. You can see it just for reference. This is Ursa Minor right here, and Polaris. And based on this picture and my observation from my car, which is not exactly precise, I'll admit, I did my best to come up with this approximate path for the meteor where it would have passed in the sky. And right near the end of the path here is where possibly some meteorites might have fallen on the ground, so somewhere just south of Algonquin Park or Highway 60. Now, what I would be curious is to know, did anybody see this fireball, and even better, did anybody capture it on camera? If you did, please come and see me. Again, that was November 16 at 8:58, just before 9 o'clock. Thank you.
Sorry, quick quick question?
Just a
Very
quick question.
Yes.
Regarding the Geminid, we intercept the tail. What's the chances of intercepting the actual object?
Oh, the asteroid?
Yeah.
From the Peter Yaniskin's book, Comets and Meteor Showers, he goes into a long length discussion on the Geminids and the asteroid, Phaethon. And as far as his study on the object, the asteroid itself will not come anywhere close to Earth until, I believe, about 80 years from now. And it'll be a close approach. It'll be possibly naked eye visibility, and that's as close as it will be. I do not know exactly what the distance is, but close enough for naked eye visibility. But nowhere near concern for impact as far as our as the next good while anyway.
Thank you
You're
very much,
welcome.
Pierre. Could we continue the questions during the break, which we're going to have next? Just a
Okay.
minor point, for those of you thinking of rushing out to Algonquin Park to search for those meteorites, they are, after all, worth a minimum of $1 a gram, somewhere between $1 a gram and $100 a gram. You might want to know what one actually looks like. And Ron St. Martin brought a meteorite about that big here today, so you can probably grab him at the break, just about the right size to make a caveman's club. So what we're going to do now is have a break. After the break, we're going to give out some door prizes. We're going to have some observation reports, some nice astrophotos to look at, and we're going to have some real science talks. So now observation reports. This is where we get to oogle over our buddy's excellent astrophotographs and sketches. First up is Murray Campbell. The rest of the observers, please be ready to come up with his drawings of Regimonti.
Yeah, whatever it is.
I'll let him pronounce it.
Okay, folks, what this is, as part of my studies of the lunar stuff, this image is of what I call demi-lune. In my study, I was looking at almost a half moon, see if I can actually pick it out. And on this particular time, I found some interesting items. One, if you look at the very top corner on the left side, you'll see a little circle that says north and south, relatively. So it gives me a rough reference for where the moon was and its lay of the track for the Terminator. And then I went about detailing it, the Terminator line and the major features along it. And when I was getting along it, you can now go into the big area there of Purbach, Regiomontanus, and the other guy who's over here. I was distracted by the Terminator. Now, immediately you think this should be belonging on some little girl's mother's fridge door. Well, I apologize for that. So this is the Terminator, upside down and backwards, of course. Purbach over here, Regiomontanus, and all the wonderful goods over here. What I found really interesting was the tonal difference between the Terminator, which was not straight, but actually went behind objects and then fell in front of this large pre-Nectarian basin in here, Regiomontanus, and this tonal difference here along the highlands. And I was trying to capture this effect, and well, like I said, this is the effect I got when trying to use crayons for something that's normally black or gray. So the detail I was trying to differentiate was the walling and the almost day-night haze that sometimes you get. You can observe, let's say, when we have a little moon sunrise excavate. So it's within about 100 kilometers, within 50 to 100 kilometers of the Terminator. I was getting this tonal difference. And that's what I was trying to capture here. So that was it.
Thank you, Murray. Next observer is Paul Commission. Paul likes to speak from the comfort of his seat.
All right. This is 7769. It's about a 13th magnitude galaxy. This is 7770. This one's about 14. And there's the main one, 7771, which is also a 13th magnitude galaxy. This is in Pegasus. It's a very interesting thing. I cheated a bit here. You notice that I took the picture before I gave it to you as a challenge object to make sure this time I didn't want that Einstein cross thing to happen again, so I made sure that you could get this. So I think it's fair this month. So this was the challenge object for the month. Thanks.
Thank you, Paul. Our next observer is Gary Boyle. Gary?
Okay, thanks a lot. Oh, one other thing too, one observations that was failed to mention at the beginning of the night is that the end of the month, end of the year, New Year's Eve, will be a blue moon, the second full moon in the same month. And in fact, it's rare to have a New Year's Eve, but it last occurred in 1990, and next will be in the year 2028, every 19 years. So here we have the Orion Nebula. Of course, I shoot a lot of the moon through the TU-Cam and sometimes using the Me DSI. And when I use my Canon Rebel XSI on a tripod, usually for wide angle, just on tripod. So I decided to use my 12-inch Me LX200, but working at f6.3 prime focus. So I took one exposure of the Orion Nebula at 15 seconds at ISO 1600. So I figured, well, pretty good results. So I took more and more. So what I did at the end for the next shot is 43 images, 15 seconds, co-edited in Registax 5 and Photoshopped to death. And this is what I got. And show Photoshop, get the nice modeling in. So why I kept the 15 seconds, so you really don't blow out the trapezium in the middle. Of course, you can go 1 minute, 30 seconds more than that, but then it's just way too bright, so I just took a lot of exposures. Learned a lot in Photoshop, got some nice detail here, such as over here, so I'm sure it'll get better. And that's about it, folks.
Thank you, Gary. Gary's picture is actually much better than what you see. The colors are very saturated and intense on a monitor screen. Very, very tasty. Thank you, Gary. Our next observer is Sanjeev Sivarulrasa. It only took me a year to figure out how to pronounce his last name.
Thanks, Attila. Well, now you're leaving too, so you have to train the next meeting chair. Since the last time I was up here, I did have one equipment change of sorts, and that is I shoot with a DSLR camera. It's a Canon 40D, and I sent it in to a company in the States to get the filter modified. And because typically the DSLRs have a cutoff filter that cuts off infrared light and a big part of the red spectrum, and that's necessary for daytime photography. But for nighttime photography, the cutting off of a big part of the red spectrum is not a good idea because a lot of celestial targets actually emit light in the red part of the spectrum, in particular H alpha. So what the modification was they took out the filter, the cutoff filter, and replaced it with a different filter that lets through a lot of the red light. So this is my first light target with the modified camera. Okay, so this is the North American Nebula in Cygnus, and this is on November 16th. I was out with Pierre and a bunch of other people who were observing meteors. I was busy shooting deep sky objects, and we actually got about 11 hours of astronomical night because, of course, with new moon in November and pretty mild temperatures, it was possible to observe pretty much all night. This is about 2 hours of exposures, and I used 6-minute subs at ISO 800. The field here is about 2.5 degrees wide, so it's just about enough to catch this object. And typically, before my modification, my camera wouldn't catch much of the red color here, or the pink color. Okay, next. I also shot the Andromeda Galaxy on the same night, November 16th. Now this is only 42 minutes. And again, it's with the filter modified camera. What I noticed the difference between my previous shot of this before the filter modification is that my camera now is picking up a lot more of the sort of reds in the middle, because the middle of the galaxy has the older stars and they're more reddish, and then the outer arms tends to be more blue. So if you've looked at very long exposure CCD photographs of M31, you would see a lot more blues and more reds than this, but I'm starting to pick up some of the color. And of course, there's your satellite galaxies, M110 and M32 there. Again, the field is about 2.5 degrees wide. And this is also as it was setting in the west, which is a pretty dark part of the sky. Okay, next, please. But 2 nights later, I went to FLO. We got pretty good night on November 18th, 19th. So this shot I did at FLO, and this is the California Nebula. It's NGC 1499. It's a pretty large object. Visually, you'd need some filters to be able to see this. The camera picks it up quite well. It's an emission nebula, and it's a pretty big object, and it's in Perseus. And at FLO, I find the best sky is really at the south and the southwest. So at this shot, I waited for Perseus to be setting. So this was between about 3 a.m. and 5 a.m. Again, it was a fairly mild night. It didn't get all that cold, although it was a little bit cold. Okay, next, please. And then this was also at FLO, but this is the Horsehead area around Orion. I shot this between about 11 p.m. and about 2 a.m. It's about 90 minutes of exposures in total. Again, all of these are with my Canon 40D with a modified filter. This star here is one of the belt stars in Orion. It's the easternmost star called Alnitak. And there's the Horsehead, that's also known as Bernard 33. That's the Flame Nebula, NGC 2024. And this one here is a little reflection nebula that's often overlooked, but it's a pretty nice one, and it's I think it's NGC 2023. Again, before my filter modification, I wasn't picking up a lot of the reds here, but now I'm picking up more of that stuff. That's it.
Thank you very much, Andrew. Please welcome our next observer, Bob Olson.
I spent some time in Florida in November, and as we're driving down I-95, as I'm driving down I-95, they launched the shuttle from Cape Kennedy, and we saw it from the start till it disappeared into space. And my wife shot this photograph from the moving car. About 10 seconds later, the shuttle was in space. It was gone, just vanished once it got out of the atmosphere. This was a photo taken at a different time than my normal exposures. This was 1,000th of a second. Okay, next one. This is M78, a reflection nebula, and it's not too far from the Orion's belt. It's sort of, instead of, we've seen the Orion's belt area where the Horsehead is, and Gary had a photograph of the M42, which is down below the belt. This is above the belt, and it's a reflection nebula, and I really like blue pictures. I think they really look nice. Okay, next. This is NGC 2403, and it's up sort of past the Big Dipper. I was actually sort of looking at M81, 82 area, and I was looking at my computer screen at what was in the area, and suddenly there's this galaxy that, holy mackerel, it was gigantic, filled my whole field of view. And so I just left my camera sitting on it for 5 hours. And so this is a 5-hour exposure of NGC 2403. Okay. This is Paul's challenge object, and it certainly is easier than Einstein's cross. My image, I think, is reversed compared to his. My camera must be. Yeah. And as Paul pointed out, there is, what would this be? 69? And 70 and 71. There's also a bunch of other galaxies showing up in here. There's this really neat little one, and I love this little one down here. And then there's one right here. So there's quite a few galaxies showing in this photograph. And on my monitor, when I really stretched the picture a lot, I could see all kinds of nebulosity. You know, the galaxy extends out quite a bit further. And every time I tried to get it in color, it just didn't turn out. So I made a, next one please. I made a black and white and then a negative image. And then suddenly, this stuff here, you can see how much the galaxy swims out here. And look at all how the galaxy's been warped and sent up this way. An awful lot of sort of other stuff showing up in the image around the galaxies. That's it, okay.
Thank you very much, Bud.
Thank you.
All right, next we're going to have an observing challenge. This is where I get to challenge you to exceed your observing skills. Now, in the past, I've been trying hard to make sure that all the observing challenges were achievable with a 16-inch telescope because Hubble has a 16-inch telescope for everyone's use. But no more Mr. Nice Guy. 16-inch telescope will not be enough. This telescope will not be enough. You're going to need one of these, preferably two. So the challenge is, what's the furthest object you can see with the unaided naked eye? So Steve mentioned that there's M31. Actually, M31 is fairly easy, and a lot of people have seen M31. You only need a suburban sky. In fact, it's a really cool thing to point out to new astronomers at public star parties, etc., that you can see something that's over 2 million light years away. But observe it soon, because it's coming toward us in only 500 million years or so. It's not going to be a challenge at all. But wait, there's more. Level 2 is hard. I have seen M33 naked eye reliably only twice. It is possible to see it. It requires a very dark sky and a lot of concentration. How many people here have seen it, by the way? There's a few. But if you make this observation, I suggest you check the telescope, because once I said, hey, I can see M33. And the guy says, oh yeah, it's easy. And I said, oh, well, I said, could you put my telescope on it? And the guy said, okay. And 10 minutes later, he gave up. He couldn't do it. He kept pointing at the same set of faint stars. He wasn't seeing M33. He was seeing the faint, unresolved group of stars nearby. So if you attempt M33 as a visual challenge, check it with a telescope. And then there's level 3. You guys recognize those objects? 81, 82? Believe it or not, 7 people have seen this visually, mostly at the Texas Star Party. Now, the Texas Star Party is some of the darkest skies on the planet, but we have some of the darkest skies on the planet in Algonquin Park, so we've got a shot at doing it too. But you will need to memorize the star field down to 8th magnitude stars, because one of those galaxies is magnitude 7. I could sort of just barely believe that, but 81, lower right-hand corner, it's magnitude 8.4, but apparently it has been seen by the toughest, most dedicated, and possibly most imaginative visual observers. That's the challenge. All right. Next, Bill, also known as the rocket guy. There's more than rocketry stuff. He used to talk about visual splitting of multiple stars. Bill?
Yeah, thank you.
The remote?
Yes, thank you. Oh, strange feeling. I went down to the clinic and got my H1N1 on this side and my seasonal flu on this side tonight, so it feels like I'm between 2 porcupines. But anyway, let me see, where's the laser? One in the middle?
Middle one.
Little one. Oh, okay. I probably don't need it, but anyway. I had intended to come down and talk to you tonight a bit about an end of the hobby that I rather enjoy. Not so much looking for nebulae or galaxies, but looking under high magnification at multiple star systems. That had been my intent. So I started compiling a list of my favorites, the Orion Nebula's trapezium, the double-double, and then going into a list of others and started looking for images. And I ran across some really interesting stuff that kind of distracted me. So we're going to talk a little bit about splitting multiple stars and then what I found on the web. Next, please, Chris. Okay, so starting out, I went to the trapezium first. It's kind of one of my favorites. I've spent some time out at FLO looking at this and trying to resolve some of the more difficult to see stars in this cluster. Next, Chris. So this is a little bit closer view of it, and you can see there's a couple more than the traditional 4 that you're going to find. There's also some that are somewhat more difficult, and I've been successful at FLO in seeing the after the more conventional A, B, C, and D stars. I've also succeeded in seeing the E, F stars, and I'm not sure whether I've seen the G or not. Sometimes I think I've seen it, sometimes I don't. However, what I found interesting, next please, Chris, is I ran across a site quite quickly that was talking about Galileo's telescope, the 23 millimeter refractor that he used in his day in the 1600s. So in particular, there's a fairly obscure part of Galileo's notes that date back to, and unfortunately I haven't written it down, I believe it's 4th of February 1641. That's just trying to remember from a different set of notes. Anyway, an early observation of his that was written about in his notes, where he not only described 3 of the stars in the trapezium, but also sketched them in the edge of the page, and along with a couple of the accompanying stars alongside. So his labeling, he used C, G, and I to identify, and he drew, not with the green coloring, of course, he didn't have green crayons in those days, but he made a sketch of the locations of them and also a couple of accompanying stars here. Now, what's rather interesting, the Rayleigh limit for a telescope of the type he was using is around 6 arc seconds. It turns out that, for example, the distance between the B and A stars is about 8.8. So it is possible to resolve with that telescope. A modern rendition of that telescope using a 4-second exposure at ASA 400 produces this image here. And the author of this website has bothered to do some adjustment of the levels, tone down the brightest and bring up the darkest, so that you can kind of see more clearly. So this is rather heavily processed from there. But you can see it is possible to resolve the B star, but Galileo himself did not actually notice that star amongst them. He did get the other 3. Now, that in itself is quite interesting, and it apparently points out that his telescope was of rather good quality. But what I find most interesting about this is the accuracy of Galileo's sketching. If one takes, Chris, please. If one takes a modern photographic image, or in this case, I think Chris has gotten us something out of a star map program, and you overlay that and take a look, with incredible accuracy, he's nailed the positions of all 5 of the stars. Now, checking up, the proper motion of all of these stars are very similar to each other, so the shape of the constellation wouldn't have changed. This is a remarkably accurate sketch. Most people, even nowadays, who sketch get the relative positioning off, are not near this accurate. So I was rather struck by the amazing level of skill shown by Galileo in his sketching, but also it kind of reminds me that I'm enjoying the same sort of pastime that he did those many years ago, and I hope all of you also can do the same. Thank you.
Thank you, Bill. Next, we have public outreach update. Bill, Mike Mockadam is not here today, but he would like us to remember that the museum is holding a star party at the here and at the observatory outside on the 21st solstice, and he'd like us to bring telescopes. We do this for 2 reasons. First of all, public outreach is a heck of a lot of fun, and second of all, we like to be nice to our landlord because they ask us to do this as part of letting us use this nice auditorium. Also, we have another report. We had a star party at Eric Ajula's kids' school, and Eric's here to tell us about it.
Hello, everyone. This was my second outreach this year, and I'll tell you, I enjoyed it even more than the first one. Pierre Elliott Trudeau School is in Gatineau, and when I was 10 years old, Pierre Elliott Trudeau was the Prime Minister. And that was the year I actually began taking an interest in astronomy, except that I didn't have anyone to turn to do that. That's all changed now. Now we have the RASC, we have computers, we have the internet, and I was telling people about how easy and how much fun it is to get into astronomy. I started by showing the IYA trailer. No one knew that this was the International Year of Astronomy. So I pointed that out to them. And after that, I showed some choice slides from the Hubble and other images that a few of which I borrowed from here, and I'll ask permission next time I do that. But they were astounded by our photographs. And they said, were those taken here? I said, absolutely, by local astronomers. And you can meet them and you can ask them questions and they can get you into astronomy. So after that, we did a tour of the solar system, and Mike, who was with me, Mike Mogadam, he did a presentation with his telescope. Can we show it? Do we have a photograph with the scope? There we go. He was set up on the stage, and because we were supposed to do a star party, things didn't work out, cloudy. So he set it up on the stage, and he used the target at the other end of the gym to show people it was a picture of Jupiter, so they could have something to peek through. And you see all the handouts there, and I had some videos, and Mike did a great job of answering questions about the RASC, and I was happy to answer questions as well. And then after that, we did a tour of the solar system. If we could go to the next picture. And I introduced these bright young students to our solar system in a very simple way with these graphics. And there was one item not on the tour, was the planet Xena, which they had never heard about. So I talked to them a little bit about that one too. Then we had a question and answer period. Questions ranging from how many times has the moon orbited around the Earth to how do the rings of Saturn stay together? So the gist of it was we were introducing them to local astronomy and how it's possible by coming here and meeting members here to get into astronomy. And it was a very successful occasion. There were about 35 people, which is more than I thought were going to show up, and especially on a rainy night. And we just had a ball. And I think I've started something at our school because in the spring we're going to actually try a star party, weather permitting, and I'm going to be asking people for volunteers to bring out their telescopes and show these young students what I didn't have a chance to do when I was their age. Thank you.
Thank you, Eric. We have an unusual segment. We didn't know what to call it, so we settled on the Space Geek Report. Please welcome Brian McCullough.
All right, thank you. Well, I was just teaching a program in the museum here, so I had all kinds of little kids to play with for 2 hours. It was great, so I'm all energized for sure. All right, this is a little something that I think it was from the Royal Astronomical Society discussion list, the RASC list. Somebody said, hey, have you seen this little animation of how the International Space Station was put together? So I thought this might be a fun thing to show. So I think really the main message in this is that to show you through this little animation that elephants can indeed fly. All right, can we run that? And it didn't go together all that quickly.
Now they want to scuttle it.
All right, some of the trusses going up, and those will be supporting other structures like the solar arrays. Okay, European Space Agency modules going on there. A Canadarm. There's an airlock, and just hanging at the bottom of that airlock is where the crew goes outside the spacecraft. In a second, you'll see a second Canadarm go on there, and at the end of it, they're going to put the dexter, that little dexterous hand. And if you look at this on the internet, it'll give you a guide on the right so you can identify which module is which, and you can click on them and you can get details about each of the modules. So you see what kind of mass that space shuttle is against the space station. All right, and down at the bottom they've shown the comparative size of a Boeing 767 and the space station just alongside it right there. All right. I didn't bring my, is this the, whoops, one of these works. So right here, this is the one of the Soyuz spacecraft. So you could bring people up to the spacecraft, up to the space station, and down. So Robert Thirsk, the Canadian astronaut, just came down. What was it this week? From the yeah, what it was 6 months, 6 months on board. All right, this one is a very similar vessel, except that it's just used for cargo supply. All right, can you scroll that one backwards? Can you do it backwards?
Just a second, I have a problem here with it.
Are you telling me like Houston we have a problem, or?
I had it going backwards until you asked now on the stage.
Oh, that's okay. Now, if only they could have put it together as quickly as we saw it here. You throw it together in a couple of weeks, and then we could have got on with the real business of space travel and got busy on the moon. So what I was going to suggest by running this backwards was if we can collapse this little Lego set, haul it off to the moon, and let's get started that way. All right, but it's well worth checking out on the intranet. And if you want, I've got a couple of some brochures and stickers about Robert Thirsk from his mission there. So just a little bit of eye candy for you. All right, thanks. Thanks a lot, guys.
Thank you, Brian. Remember that tickets from the ISS are available to ordinary people for the small sum of $30 million. We won't be selling them in the back tonight. Next, this is the section of the meeting where we talk about big science and real science. Please welcome Neil Rowlands for the 10-minute Astronomy News Report. Neil?
Well, hello, good evening. So I'm just going to give a quick update of some things that caught my eye over the past 2 months, probably. In particular, I had a couple of science papers in my briefcase for a while, meaning to read them because it was interesting stuff, and this finally gave me the opportunity to read them and find out. So that's the water on the moon. I'm sure you might have heard some recent press on this aspect. In fact, there were 3 papers published in Science magazine, October 23rd, and they were reporting on results from 3 different spacecraft. You had the, let's see, the Cassini spacecraft, Deep Impact, which were both flybys of the moon, and then this was Chandrayaan-1, which is India's first foray to the moon, and that was an orbiter. So here's what these all 3 probes were trying to do, was use this feature, an absorption feature, from the reflected light of the moon, and determine if, in fact, there are these absorption features which would indicate possibly ice, water, or the OH ion, all related, and hence all give a related spectral dip here. So it's not much. You can see here, you only see like a 5% dip in the spectrum, and this is at a wavelength about, well, it's 3 microns, or 3 times the longest wavelength the CCD camera could see. So all 3 spacecraft are equipped with spectrometers to do that, and so did they find anything? Well, yes they did, but you have to process the data quite a bit to see it. Here's actually, this is data from the Deep Impact spectrometer, and this is a global average spectra. There's 3 cuts through the lunar disk, and this is what the lunar disk looked like when the spacecraft went by, and produced these 3 spectra, and you can see this absorption dip here. This is reflected light, but the reason it's increasing in as you go to longer wavelengths is there's some thermal in here too, so you have to take out the thermal background. So when you do that, you end up with these dips, and lo and behold, these are features of the of hydrated aspects of the lunar soil. So it's OH and water. And here on this side is the data from the Cassini flyby, and actually this is quite old. This is from 1999. When Cassini was using the moon Moon Earth system as a gravity assist to get to Saturn. So I guess it just sat in the archives until they pulled it out to support the data from the other missions. So here it's very important, as I said, to get the temperature. So here's a plot of the temperature of the lunar surface when these observations were made. And then this is a plot of the depth of the band, how much absorption in blue here, and this is the 3 micron band. So this is both the water and hydroxyl. And then this, this is more just the water. This is the OH primarily, which provides a sharper band. And then this is a combination in red here. So that's the global distribution, if you will, from this snapshot that the Cassini mission took. And they tried to compare that with a map of the hydrogen, map of the suspected hydrogen coming from Lunar Prospector from 1998. And basically all they could say really is that, well, there were some positive correlations and some negative correlations. The hydrogen map is probably coming from stuff much deeper, whereas the spectrometers we're talking about are just really looking at the first few, microns, if you will, of the lunar soil. So the other thing, so it was very promising. We seem to have detection of some water, and in fact, the estimate though is pretty wide. So you're talking about anywhere between 10 parts per million to 1,000, and that's quite a bit more water. If it's at the upper end, that's quite a bit more water than they found in the Apollo rocks. So it's kind of an interesting result. Going further, the Deep Impact mission provided a better, even more data. It provided a spatially resolved spectra of the disk, and this is the distribution it found. This again is temperature, and this is the depth of the water feature. So it seems to, I'm worried about this one a bit because it seems to anti-correlate with the temperature, so it might mean that there's, but the other thing is that this paper has concluded that the absorption tends to dissipate, if you will. You don't see as strong a feature as the lunar day progresses. So during the lunar night, or dusk or dawn, you get a deep feature, and then that feature tends to wash out, deep absorption feature, and that tends to wash out as the day goes on. So this is what this graph is showing with some pictures from a later time, and showing that the band actually changes, which is also interesting. I think basically it means that whatever it is, the hydration of the rocks tends to change during the lunar day, and kind of makes sense, I think. I think it's analogous to just dew forming in the morning and then dissipating. However, that analogy is orders of magnitude out for the amount of water we're talking about. We're talking about a very slight amount of water, most 1,000 parts per million. So the other view, which got everyone pretty excited, was this one from the Indian mission. This is a Moon Mineralogical Mapper, the M3 instrument that's provided by the United States to India, and it provided basically a much closer view. You've got now, whereas we were looking before at views of 170 kilometers per pixel, now we're looking at 140 meters per pixel. So this is in orbit. You get a much better view of the surface, and here you're getting maps that are built up from thousands of these images, and of course you need your temperature map to have any hope of characterizing the absorption feature out here at longer wavelengths. Notice that it cuts off right around where things get interesting. So that was unfortunate, but it's why they asked, in particular, the deep impact data to be taken. So they produced a nice map here. This red is, I think, around 1,500 nanometers. It's mostly feldspar type materials, indicative of the highlands, and then the blue and green are more indicative of the silicate minerals, which are from the mare, the lunar seas. But of course, what got everyone excited is this hint of an absorption feature at long wavelengths that is certainly concentrated to the poles. And moreover, when they look at it in detail, it's also concentrated to the shadowed regions. This is an image of the band depth, and you can just start to see that perhaps there's a bit more intensity in the band in the shadowed regions of this crater. This is a normal image, and then this is the 3-micron feature. And also some here, too, where the ridge, shadow of the ridge. So kind of exciting. So what does it all mean? It means the moon isn't completely dry, or as dry as we thought, but it's still not clear there are any significant concentrations. But because there might be this diurnal cycle of migration of these hydroxyl ion or the water, it's possible, I guess, that some of this is collecting in the lunar polar regions where you have more shadowed craters. So of course that's what everyone's interested in, and we'll have to wait until the final results come out from the L-Cross mission, where they crashed the spacecraft into one of those craters at the South Pole, I think, of the moon. The result, it looks promising, I guess, but the result is probably a bit early yet to say how much is there. But it'll be interesting. If those measurements correlate with these, then it means that the water isn't necessarily collecting, and hence there aren't any really good, valuable concentrations of this resource. But it was interesting, the popular press, it was all over the place. I think initially, of course, a lot of hype about the water on the moon. It's nice to go to the articles and actually see what's going on. I noticed there's a quick summary in this month's Sky and Telescope that was going almost the other way too. Very pessimistic assessment of it. So I thought I'd just hit a couple other items that were of interest in the news lately. Kind of related to the last topic is that the HiRISE camera on the MRO, Mars Reconnaissance Orbiter, we're going out in the solar system now, has found this little thing on the surface, and it is the Mars Phoenix lander, which it actually imaged before in frost-free times, and this is, I'm still amazed by this picture. I mean, you can actually see the solar panels and the main body of the orbiter, and that was taken, well, must be a year and a half ago now, and that's just obviously a computer-generated picture of it, but man, does that look look nice. I mean, you can actually take that from Mars orbit. It's incredible. So they revisited it, and lo and behold, the carbon dioxide frost is all around, probably covering the lander too. As expected, the lander is not operational. It wasn't intended to be. It was just to examine that region of Mars, you know, as winter approached. Winter is now, actually this was back in August. The MRO had a bit of a glitch with its systems, so they're still trying to figure out how to restart things and restart science observations. But this is one of the last things it did, and lo and behold, found Phoenix for us. Just to remind everybody, Phoenix, of course, landed right on top of what looked like deposits of water ice, was able to dig up some of them, and it subliminated as soon as it was exposed, so that's why you don't see it on the surface, but it's right there just under the lander. And of course, the Canadian contribution there was to have a LiDAR system that went up in the atmosphere, and this is a plot of height versus time, and these streaks here are basically fall streaks of material starting to precipitate out. It doesn't hit the ground in this case, but that was snow on Mars. So Canadians discovered snow on Mars. How appropriate. But it still amazes me that they have all this equipment at Mars that can do all this. So the other news item I thought should cover is Herschel, or the Herschel Space Observatory, launched by European Space Agency, has launched the largest telescope, 3.5 meters in diameter. It's a sub-millimeter telescope, and it's cooled behind a sun shield. And it's finally passed its commissioning and is now producing some great data. And there's been some press announcements. And in this particular, this instrument, HiFi, there was a Canadian contribution to that, a local oscillator. And actually that helps result in this spectra where they tune the local oscillator on, if you just detune and tune to either side of the line, and actually are able to record data at all times. This is a Fourier transform spectrometer. We're up at a few hundred microns, I guess, and finding elements, molecular species in molecular clouds. This is an image from a Space Infrared Telescope facility. But Herschel's all about kind of cold to warm interstellar matter. And moreover, they want to use this now in other galaxies. This is our galaxy, but other galaxies will be revealing their secrets in terms of how stars are forming, how the molecular constituents are churned up and disassociate and come back together. And this was a spectacular picture. I thought this is the other two instruments on Herschel in imaging mode. This is Spire and PAX. And you think, oh, great, nice color picture. Well, it's the blue is indicative of 70 microns. That's 70 times the wavelength of the longest wavelength the CCD camera can see. And then it just goes on from there. I think green is about 140 microns, and then the red is 300 to 500 microns. And this is inside a dark cloud. Basically, a visible image is just an opaque spot in the plane of the Milky Way galaxy. And here we see all this action, all this pre-star forming activity, if you will. So that was it. Some news items from recent past.
Thank you very much, Neil. Our next speaker is Simon Hanmer. Please welcome Simon.
Thank you. Chris, can we do this in our usual tandem? Let's move to our first slide here. Okay. Now, a couple of years ago, I talked to you about NASA's Stardust mission. This mission was to investigate what the comet, I guess we would call it Wild 2, but it's actually really called Wild 2, what that comet was actually made of, and especially paying attention to the rocky components of the comet, and the surprising new perspective they give us on the development of the early history of our own solar system that we as amateurs are able to observe through our telescopes and through our binoculars. Now, what they found was extremely puzzling. The comet contains dust from the inner part of the solar system, associated with ice from the outer part of the solar system. And so that suggests that the accretionary disk that the solar system itself was formed from had undergone some kind of mechanical mixing in the early part of its history. Now, this created a major headache for planetary scientists who've been looking for a mechanism that would allow this mixing to happen. But recent work, published in the prestigious scientific journal Nature, has come up with a possible solution that actually makes a lot of sense, certainly makes sense to me as a geologist, and that's going to be the subject of my talk tonight. But let's start by reminding ourselves of why the stardust results were so problematic in the first place. Next one, please, Chris. Now remember that the solar system formed 4.5, more precisely 4.65 billion years ago by the condensation of a central star and the accretion of its attendant planets from the solar nebula. The solar nebula, of course, is a rotating, or was, a rotating accretionary disk of gas and dust. Now, the solar nebula had a marked thermal gradient with cold outer reaches beyond what we now see as the planets, which is where we know that the comets actually formed. And the important point to retain here is that the comets are considered to contain ice and dust representative of that early solar nebula. In other words, they're essentially dirty snowballs. And the question is, where did that dust come from? And to answer that question, we need to know what kinds of dust occur in comets. Next one, please, Chris. So what did the Stardust mission actually find when it looked at Comet Wild 2? Well, it found two kinds of dust. These are called amorphous and crystalline. And it's the crystalline dust that created all the headaches. So let's see why. Next one, please. Now, in crystalline materials, atoms are neatly aligned along planes in three-dimensional space with a predictable regularity. And when you extend this microscopic regularity to the macroscopic or the visible scale, that's why crystals actually form reproducible and diagnostic shapes. Now, although this image I'm showing you here is a very simple arrangement of atoms, to illustrate the principle, sometimes these arrangements can actually be far more complex. And this would be the typical case of the silicate minerals such as olivine, pyroxene, feldspar we heard talk about earlier this evening, and quartz, which are common minerals in both the rocky planets, in asteroids, and in meteorites throughout the solar system. Next one, please, Chris. Now, on the other hand, what they're called amorphous materials, they have a random atomic structure. In other words, there is no internal order, and hence they do not form crystals at the macroscopic or visible scales. That's what amorphous means. It basically means that they have no form. And the commonest example of this, which you'll all know, is actually glass. And glass is, in fact, in reality, a frozen liquid. Next one, please, Chris. Now, here's the trick. Stars eject enormous quantities of dust, including silicate dust, and especially when they puff off their outer layers either as planetary nebulae or when they actually explode as supernovae. Now, although these stellar dust grains initially form as crystalline materials with well-ordered internal atomic structure, they hang around in interstellar space for quite a while before getting caught up in a second cycle of star formation, such as the events that formed our solar system from a solar nebula at 4.6 billion years ago. The problem for crystalline dust in interstellar space is that it's exposed to the bombardment by enormous numbers of subatomic fragments called cosmic rays, which of course are not really rays at all, they're bits of atoms. And these disrupt and randomize the initially well-ordered structure, atomic structure of these crystalline materials, and the resulting internal structure of these tiny grains of dust is therefore amorphous. So amorphous says to us interstellar dust. And this is the kind of dust that ends up in the solar nebula from which a solar system such as ours eventually forms. Next one, please, Chris. So where does this crystalline dust come from in comets in our solar system? Well, this is where this latest article from the Nature paper comes in. The latest idea there is based on recent observations of stellar outbursts in young stars surrounded by accretionary disks. In fact, one in particular, disks of gas and dust, one in particular that really closely resembled our early solar system. And these outbursts are explosive episodes that occur during periods of increased rates of accretion of material onto the central star, which give rise to short bursts of heat in the inner part of the accretionary disk, with temperatures that, and this is the important point, that temporarily can reach over 750 degrees centigrade. Now, by analyzing the infrared spectrum of the accretionary disk, these scientists showed that there was a short-term increase, and that's the other important bit, a short-term increase in the presence of crystalline dust in the grains of the inner part of the accretionary disk, and that coincided with the stellar outburst in time. Next one, please, Chris. So here's the problem. We all know, we also know that the solar system is chemically zoned. And this is pretty obvious by simply looking at an image like this. We can see the rocky planets in the inner part of the solar system, and then the gas giants and the ice giants as you move out through the solar system. So the planets that formed near the sun are still near the sun, and those that formed further away are still further away. So the problem can be stated in this way. How do you mix interplanetary dust, but not the planets themselves? Next one, please, Chris. Now, the only reasonable solution here is that the dust components of the early system were thoroughly mixed up, thoroughly stirred up, such that the crystalline dust of the inner solar system got mixed up with ice and the amorphous dust that was located in the outer reaches of the solar system. However, if you're going to propose mechanically mixing the solar nebula, this is a huge piece of real estate to be messing with. The outermost parts of the solar system, where comets formed, and where they still hang out with dwarf planets, the areas known as the Kuiper belt and the Oort cloud. Here's the Kuiper belt here, this plane in here, and then this big spherical ball out there is the Oort cloud. This real estate reaches a quarter to halfway to the nearest star. On scale-wise on this, the solar system as we consider it, in other words, the planets and the sun, are in there somewhere. So we're principally concerned here with the Kuiper belt because it's a lateral extension of the accretionary disk of our solar system, but the Oort cloud also contains comets, so it can't be ignored. However, since I don't yet understand the genetic relationship between the Oort cloud and the Kuiper belt, the Oort cloud will have to be a topic for another time. Next one, please. Now, when we discussed this issue 2 years ago, I suggested very simplistically that the mixing of the solar system materials was size dependent. And you may remember the analogy I gave you. I said, well, think of 4 cars, the rocky planets, 2 16-wheelers, Jupiter and Saturn, and 2 buses, Neptune and Uranus, lined up on a bridge in a dust storm. The dust will get stirred and mixed, but the vehicles won't change place. Now, this really just begged the question, what was the process that mixed the fine-grained dust in the first place? Now, 2 years ago, I had to admit we had no answer. But in the same issue of Nature I just mentioned earlier, someone has finally come up with a plausible theory. Next one, please, Chris. And here it is. The fundamental problem is that radiation pressure, in other words, the pressure of light from the central star, in a solar system, is too weak to push crystalline dust from the inner part of the accretionary disk to the outer part where the comets form, if it has to do so through the traffic jam represented by the central part of the accretionary disk itself. Remember, 4.6 billion years ago, the space between the actively accreting planetary bodies was not as we see it today. It was jam-packed with gas and with dust. Now, planetary scientists have come up with several ingenious ways to get around this. These include turbulence, magnetically induced winds, and complicated spiral geometries, all occurring within the accretionary disk. But they all have problems of one kind or another, and I won't get into the details of that here. Suffice it to say that none of them actually work. The latest model, though, as I'm saying from this Nature paper, as shown here, is elegantly simple. And it proposes that infrared radiation, which is a fancy way of saying heat, from the dust in the central core of the accretionary disk, shown here in red, this is the meat in the sandwich, if you like, that heat, that infrared radiation, actually lifts crystalline dust of certain grain sizes to the outer surfaces of the disk, the accretionary disk, shown here in blue. And this is Out there, this is where the weak stellar radiation pressure can more easily push the grains to the outer part of the disk, basically because there's less stuff in the way. Now, the spacing of the yellow arrows in this diagram and the gradation here of the colors illustrates that this sifting and lifting is strongest in the inner part of the accretionary disk and decreases outwards along the thermal gradient, which explains why the thermal dust grains eventually drop back into the disk where they mix with the rest of the stuff that goes to build comets. The end result is comets that form in the cold outer solar system and that incorporate both amorphous, interstellar dust, and crystalline dust from the transiently, this is the key word, the transiently superheated inner parts of the primeval accretionary disk. Next one, please, Chris. So the first take-home message tonight is this, is that NASA's Stardust mission was highly successful in providing new observations that got planetary scientists thinking about the dynamics of solar nebulae and the evolution of accretionary disks in general, as well as that of our own solar system. That's not bad for a fairly low-cost experiment by NASA standards. But the story doesn't end here. There are two more take-home messages. Next one, please, Chris. In another Nature article published this summer, planetary scientists took a new look at the main asteroid belt, which sits between Mars and Jupiter, somewhere around about here. Next one, please, Chris. Now, this is a very artificial representation of the main asteroid belt, seen from a perspective way up above the ecliptic plane of the solar system. That's the plane in which the planets orbit the sun. Next one, please. And this is just as artificial a representation of the main asteroid belt, looking from the side. In fact, you're looking towards the sun from about the distance of Jupiter. Next one, please, Chris. Now, the main asteroid belt, many of whose members, including the dwarf planet Ceres, indicated down here, are easily observable by amateur astronomers. And this is, the belt is easily observable by us, that's my point, and it's raised fundamental questions regarding the origin of the solar system ever since it was first identified. Some asked if it was populated by a shattered, mature rocky planet, while others wondered if it was made of primitive material that never got its act together to make a planet in the first place. And it turns out that it contains both mature and primitive material, and that primitive material is indistinguishable from dead comets. So this raises the following fundamental question. What's all this comet-type material doing in the middle reaches of the solar system, given that the comets formed in the outer part of the solar system? Next one, please, Chris. Now, it's well established that a computer model of the solar system called the Nice model, Nice after the town in southern France where it was first formulated, predicts that about 4 billion years ago, the giant gas planets, Jupiter and Saturn, migrated inwards towards the sun, while the giant ice planets, Neptune and Uranus, migrated outwards towards the Kuiper belt. And this is what gave rise to the great bombardment that came to an end about 3.8 billion years ago. Gravitational effects due to Uranus and Neptune, known as resonances, destabilized the orbits of dwarf planets and cometary objects in the Kuiper belt, and either ejected them out of the solar system or channeled them inwards towards the sun. And some of them left their mark in the major impact features that decorate the face of our moon and that Murray was showing us earlier, that we can observe directly with just about any amateur equipment, telescopes or binoculars, while others were shepherded by resonances with Jupiter and Saturn into the main asteroid belt, where they joined the debris left over from the rocky planet formation in the inner solar system. So here's my final slide. So the second take-home message is this, is that the textbook picture of our solar system as a collection of stable orbits, chemically zoned from its warm interior to its cold exterior, is actually way too simplistic. Our solar system has evolved dynamically, initially ejecting dust from its interior to its exterior, where it mixed with material derived from interstellar space. And that was followed 700 million years or so later by planetary migration that hurled outer solar system material back into the inner solar system, where some of it took up residence in the main asteroid belt. Now, with all this mixing and migration, it's a wonder that our solar system is as stable as it is. And in addition, these models proposed here to explain this dynamism require systematic and gradual changes, changes that do not give rise to a major instability within the overall planetary system. And this is, frankly, nothing short of miraculous. So the third and final take-home message is this. It's not unreasonable to ask how representative our currently harmonious solar system really is of planetary systems elsewhere in our galaxy. And I leave you with that profound thought tonight, and thank you for listening.
Thank you very much, Simon. Thank you, Simon. That constitutes the big science portion of the program. And now I have a surprise award presentation. This is the Chairman Wins Award because I just made it up. Actually, it's not a complete surprise. In the February meeting, I mentioned that I liked construction talks and wanted to encourage them, so I said I would give this out to the person who presented the best construction talk this year. And so my pick, which I don't have to justify to anyone because I came up with the prize for best construction talk, was Tom Butterworth's talk on the South Nation Space Station, where he constructed a observatory dome in his garage, probably annoying the heck out of his wife, but he didn't say that. Oh, that explains why. Tom? And while I'm on the topic of just making things up, I've been most impressed with the great many people who came together to put these meetings on, but there's one person who stands out in the huge volume of work that he has done, and I don't have a slide for him, but I'll just read out this plaque here, because I don't have a picture of it. It says, the official looking RASC 2009 Children's Award for High Tolerance for Pains in the Neck and PowerPoint is awarded to Chris Tarrant for dedication well beyond the call of duty. And just so you can see at the bottom here, I faked up 5 X-ray photographs of necks detailing specific as to where the pains in the neck are, and they do things like too much PowerPoint, too much email, putting up with the speakers, worst of all, putting up with the chairman. It would be my honor if you accepted this, Chris. So I said, need to make a joke at his expense. All right, so the nominal portion of the meeting is over, but there's still plenty of fun to come. After the meeting, please join us for carbohydrates and caffeine with Arthur and Ann Fraser. Here's your chance to speak to our speakers and ask them questions. Please stay in the lobby only, the rest of the museum is closed. You may also want to pick up a copy of the observer's calendar if you haven't already done so. And later tonight, some people will be going to Kelsey's for some real food and possibly a little alcohol. And remember, on the 21st, we're going to have a star party here at the museum. And I'm supposed to come up with a clever quip at this point, but I'm all out of clever quips. You realize what that means? It means it's time to upgrade chairman. So at this point, I would like to pass on the symbol of the chairman's absolute regal authority over the meeting to Bill Wagstaff, your next chairman. The chairman's power is limited to deciding when everybody goes to the bathroom at the same time. But it's now your meeting.
Well done, Attila. I have done, thank you. I'm all prepared. Thank you very much, Attila, for your I would like to ask everyone, to consider Attila's years of service to the center, but especially his last year in service as the meeting chair, and thank him very much for his time and effort.
This next slide, Chris.
Okay, next meeting is Friday, January 8th, not the first of the month since it's a holiday, but the 8th. And
next slide, please, Chris.
Let me see. For the next meeting, we'll be holding a swap meet before the meeting to start at 7:30 p.m. If you have any bits and pieces you want to get rid of, looking for a special deal on just that little widget you need right now, then come on down early, and it'll be right here on the stage. Next, please. And this evening's attendance was 117 people. Thanks to all of the organizers and speakers. You can read all the names. I don't think I'll run them all off for you. Let me see. And thanks to our host, the museum. And to everyone, good night.